Yeah, so I'm going to talk a little bit about how I use scientific computing tools in Python in the course of my normal work. And first, let me give you a little bit of an introduction into how I've been using scientific computing in Python through my career. I started out maybe 10 or 11 years ago as an undergraduate at Penn State. There weren't that many scientific computing tools in Python at that time, but I was using it more as a scripting language to find data files to then make driver scripts that would submit it to a large cluster that they, for some reason, gave access to an undergraduate, which was great. I moved on to graduate school, and our group got more and more frustrated with the tools we had for plotting, and so we gravitated more and more towards using Python tools, and like 80% of the plots in my thesis ended up being generated by Matplotlib. And then I moved on to a really small radar consultancy firm, and it was there that we made images out of radar data, and that involved a lot of image processing and signal processing, and so I was doing a lot of Fourier transforms at that point. All along the way, there's been a lot of side projects for scraping the internet for data about movies and sports in order to make visualizations from that data, and I fell in love recently with the Pandas library in order to organize and just clean and work with all that data. I've done a bunch of machine learning competitions, specifically on Kaggle.com, and use that as an opportunity to learn about machine learning and specifically the great tools in Python, scikit-learn, that allow you to do that very easily. And yeah, so I'll talk a lot about the rest of the functions I've been calling at Endgame. So what do I want to do there? Well, what we want to do is we want to maybe make a baseline of what someone's network or what their computers are doing normally, and then we want to highlight to security professionals when that behavior becomes abnormal. And so, for example, here are two examples of why that abnormal behavior might be an indication of a security event. For example, a high number of connections might be an example of a brute force attack, or a large volume of data leaving a certain IP might be an example of an exfiltration event. So what am I doing to try to solve that problem? Well, I'm trying to build a system that can track and store historical records of any metric that I can come up with, anything that I can record from a network or a computer. And then once I have all that data stored and easy access to it, then I can develop algorithms that will detect abnormal behavior and try to minimize false positives. In this realm, false positives are really the main problem, because when we bubble up alerts to the user, that we want to be saying, like, this is something you should investigate, this is something you should spend time on. And if we start giving the users something that it was a dead end or it wasn't really worth their time, then they're really going to lose trust in the product. Okay, so this is an outline of what I'm going to talk about. First, we need to gather the data, and those are the three Python projects that I use to do that, to help me gather and store the data. And then I'm going to talk a little bit about what models I build and what scientific computing tools I use to build those models. Okay. So here, this is a general overview of my data flow. I'm going to start at the end. What I want to eventually have is just a fast and easily accessible database for all the time series data that I've collected. And we have a large volume of data coming in, but once we evaluate it for metrics and kind of store it all together into just time series, at that point it's a much smaller volume. And that's why I can use Redis, which is just an in-memory database. It's an in-memory key value store, because at that point my data size isn't that large. And so I fill that database through two methods. One is I go through historical data and kind of try and backfill the time series based on the data that we have collected. We store data in a Hadoop distributed file system, and that's just a way for a cluster of computers and to use their hard drive and kind of store data in a repeatable and fault-tolerant way. And so yeah, I'll talk about the Python projects I use to read data from there and backfill my time series. And then I also, in real time, get the messages as they come through our data flow. And we use the Apache Kafka project for that message passing. And I'll talk a little bit about how I can subscribe to messages there in Python. So first, the Python project I use to manage that time series database is called Kairos, and it's an interface to a couple different backend storage databases. I'm using Redis in my case, but there are others available, and it's tailored for time series use. And what really drew me to using this project is just its easy interface. It's really easy to use. The syntax is very clear, and also it takes care of expiring data, and there's different types of time series. You might want to store counts, or maybe just there's different values as they come through, and you want to get the mean in each time bin. And Kairos makes that very easy to use. It's open source by the good people at Agora Games, and you can find it there. So yeah, I'm just showing you some example code of how I use it and how the syntax is very easy. I have a lot of example code in the talk, and I've kind of ripped out some of the error checking and uglier things to just show what the simple interfaces to these projects are, just distill it to exactly how they're used. So the first thing, can I point here? Yes. So the first thing I do is define some time spans over which I want to record the data. And here I want a lot of granularity on a shorter time frame. That's that first entry there where I want bins of just 60 seconds and enough of them to span just 2 days. And then I can also define as many of those time spans as I want. What the data that I'm going to be showing you later in the talk is mostly from this coarser granularity where I store data in 30-minute time bins over a period of about 3 months. Yeah, so then after defining that in a Python dict, you can just feed that into your Kairos object here, along with your connection to the Redis client, and you're off and running, and you can start really easily defining metrics and filling the values with just this easy function call here. So yeah, the first way I fill that database is through in real time by a Python interface to the Apache Kafka project, where Kafka is just a publish subscribe messaging rethought as just a commit log. And it's distributed in order to handle really high throughput of incoming data. And yeah, and you can, this project is available there. It's a Python interface to this Apache project, and here's the simple interface to it. After establishing a connection to the head Kafka node, then we can just define our consumer. We specify the name. My project is called Time Vault, and the type of messages that I'm interested in, and then I can just simply loop through them. And this Kafka Python project and Kafka itself takes care of all the details. And I've kind of hidden a lot of the data processing that I'm doing in that insert to Kairos function call, but really what I'm doing is just translating the JSON into native Python objects and then checking those Python objects against a bunch of metrics that I've defined, and then filling my Redis database. And I think I'll show you a little bit more of that detail here when I talk about this batch historical filling. In order to do that, I use pyspark, which is the Python interface to the Apache Spark project, where Spark is a fast and general engine for large-scale data processing. And yeah, this is a great project. I think I'm going to take a little bit more time on pyspark just because I've really loved using it over the past couple months, and I haven't heard a lot about it at this conference. And I think maybe for people's problems, if they're dealing with large amounts of data, I think you should really take a look at Apache Spark. It's written in Scala. It has interfaces in Scala, Java, and most crucially Python. And it really just makes it very easy and expressive to write complicated data flows that just easily get distributed out among a large cluster of machines. And yeah, I really love it, and go use it. So yes, I'm using it to backfill my time series database. This is the example code here. Again, it's setting a connection to your head node, and then and then getting a list of the files. Getting a list of the files and reading all those, and then just going ahead and defining what it is that I need to do against each of all the data that I'm running over. The Spark is lazy in evaluating things, and it's not going to do it unless you need an actual result, and that's why I'm counting after inserting everything into my database just to force it to execute. Yeah, I wanted to go into a little bit more detail just to evangelize about PySpark, in that, like, this is kind of all the detail that I was kind of hiding in that insert to kairos function. And even though it's a little bit more complicated, you know, showing you all the data flow, it's really easy to express in the PySpark's syntax. And yeah, you can see here I'm loading JSON and taking a message that includes a bunch of individual elements that I need to process on, and just flattening all those out. But even with this complicated processing, the syntax is very easy. So the end result is a database in Redis that I have easy access to. This is the interface to Kairos to grabbing that data, and it's just 2 lines then to dump that into a pandas data frame that has a datetime object as my index. And once I have that, I mean, it's really easy to go ahead and try different algorithms and process my data. And what I'm showing here is just some example. So this is the number of times a certain IP is responding to connections that are requested of it. And like I said, this is the Corso data over about 3 or 4 weeks. So now that I have the data and it's easy to access, let's start building some models around it, and let's start with something stupid, where we just take all the data up until a certain point and just calculate the mean and standard deviation, and then alert a user when the actual data is far enough away from the mean by a certain number of standard deviations. And so let me explain this plot, because a lot of my plots are going to look like this with the same sort of legend. The actual data coming in is in blue, and then the prediction window is in green. So the center of that green band right there is actually the prediction, what I think the data should be based on this model. And then that green band expands by 1 standard deviation. And then when the actual data is far enough out of that band by a configurable number of standard deviations, that's when I'm actually going to alert the user, and I show that by those vertical red lines. That didn't really fit the data very well. Let's go ahead and do something else. Maybe fit a sine curve to the data we've seen so far and calculate the standard deviation based on the residuals to that fit. And so now, our band around the data is getting a little bit better, but we're just failing on weekends, and there's some things that we could be doing better. So based on all that, let's how should I be doing this a little bit more complicatedly? And the way I went ahead and did that is by classifying the different time series. Like, everything is going to be behaving differently. There's certain metrics that are going to look like what I just showed there with daily and weekly patterns, but there's other metrics that are just going to be totally flat. So when classifying these different time series, I wanted to answer 2 questions, and they're what I just said there. Do these time series show weekly patterns, and do they show daily patterns? First, I'm going to talk about weekly patterns, and really the only thing I'm doing after answering this question is, should I split up the data that happens in weekdays from the data that happens in weekends? And this is the method I use to do that. I fit a sine curve separately to the weekday and weekend periods, and then take a ratio of the level of those fits. So this is how I do that in code. I'm fitting this function here. This is the overall level of the fit that I referred to in the previous slide, and then I also fit the amplitude and a little bit of a time delay. And I'm using the SciPy excellent interfaces to minimization routines in order to get the best fit parameters here and return those. And this is the function that goes ahead and splits that up and does that for for my data on weekdays and weekends, and then yeah, I take the ratio of those levels. And again, I have a configurable cutoff so that when those levels are close enough to 1, then I lump all the data together. I assume everything's the same, and if not, if it's outside of that window there, then I need to split up the data and do a different analysis on weekdays and weekends. And here I just showed a plot of the fit on two different time series that I have. And here you can see the level of the fit on weekdays is much greater than weekends, and on this different time series that behaves differently, well, it's close enough together that I think I should lump all this data together. I don't think I mentioned what this second data I'm throwing at you is. That's just the response size to a certain IP. After every connection request, we record how many bytes are leaving. And so here I'm showing in each time bin what the mean of that response size was. And for this machine, we expect it to be relatively constant, but you see it's a little bit all over the place. But it shows different behavior than the time series above. And that's really what I want to work on this classification here. So now that we've done that and decided whether or not to split up data between weekdays and weekends, then I want to decide if these time series show a daily pattern. And the way I do that is by taking a Fourier transform and inspecting the bins associated with the frequency of a day. I take the 3 bins that are around that day frequency and add them up and compare them to the first bin after the Fourier transform. And that first bin is called the DC component, and it characterizes how much energy is just in a flat, just in a flat evolution. So here's a plot of what that looks like. In the last few slides, we decided that we want to split up the weekdays and weekends of this time series. So this is the weekdays just all smashed together. And after taking the Fourier transform of that, it looks like this bottom plot in green. And I'm highlighting in those red vertical lines the bins that are associated with the frequency of a day. And so I'm adding those up and comparing them to the first bin. And in this case, yes, the algorithm returns what we'd expect is that there's a strong daily pattern here. And so this in blue here is just the weekends from that same time series all smushed together. And after taking the Fourier transform and inspecting it, it looks a lot different. And after summing up the bins associated with the frequency of a day, you can see that the ratio is going to be very different, and this algorithm is going to decide to I'm going to do something differently that I'll describe in the next few slides. This is the code that goes ahead and does that. Here I'm finding the bin associated with the frequency of a day because there might be different numbers of bins and then different bin sizes. And so yeah, I use this relation to relate the bin sizes in the time domain to the frequency domain. And then I go ahead and call the Fourier transform and return the ratio. Okay. So after I've done that classification, I want to go ahead and apply a smarter model than what I've shown before. And what I've done for that is an exponentially weighted moving average, of which there's an excellent support for calculating in pandas. And what this is simply it's a moving average that weights data that has occurred recently just more heavily than data that has occurred farther in the past. And the relations for that is shown here. The decay parameter shown in alpha here, it was a little different than what you specify in pandas. In pandas, you'd specify the span that's related to alpha by this. The span is kind of, it's about how many bins are like important in the moving average fit. So you can say, oh, I kind of want the 10 most recent bins to be important, so you set your span to 10. And okay, so if we have classified the data to not have a strong daily pattern, then we just kind of blindly apply this exponentially weighted moving average. But if it does have a daily pattern, then I do a stacked analysis that I'll describe later. And this is the code for carrying out that analysis. The pandas function calls are right there, and then what I'm doing in the next couple lines is seeing how many standard deviations away from the moving average prediction the actual data is, and then cutting on that and highlighting when that data is far enough away from the prediction. And here is just a new data set that kind of shows this algorithm working well, kind of in maybe the best case scenario. And you see that it's very flat and has well-predicted behavior, and thus the standard deviations can get very narrow around the actual data. And we can alert when there's really just small differences that from the well-defined behavior that has occurred previously. And then, yeah, you can see the bands of our predictions expanding as the behavior goes crazy. And then this is an example of that same algorithm working on the data that I've shown before. And this is with different span parameters and also different standard deviation cutoffs. And it's an open problem now that I'm working on how to best determine what those two parameters should be to minimize false positives and alert on the things that we want to alert on. If the data has shown a daily pattern, then I go ahead and do this stacked analysis. And so what I'm going to do is really just take the weekdays alone and group by time of day, and pretty much just stack each day on top of each other. And that's what I'm going to show. That's what I'm showing here in this scatter plot. The x-axis is the hour of the day, and then it's the same y-axis as what you've shown before. And so what this analysis does is, maybe let's say like at just 8 a.m., there's a certain number of connection requests to this IP, and that number at 8 a.m. can evolve over weeks, over a number of days. And so what I do is highlight just the data in that bin and look at how it evolves over a couple days. The x-axis here is days, and this y-axis is really the number of connection requests at 8 a.m. or in one bin between 8 a.m. and 8:30. And then so once I've highlighted that data, then I just go ahead and do the exponentially weighted moving average, just with different span parameters. Yeah. And here is the code that I used to do that. Pandas makes it really easy to group by day, and then go ahead and apply the Pandas functions for moving average and standard deviation. And then I have a lot of code here to just take the results of that and put it on top of the original data frame that I had. And here are the results of that analysis. And now you see that the predictions and my prediction window is following the data a lot more closely. And yeah, I'm just making better predictions about the data. So I'm currently investigating also using autoregressive integrated moving average models to make better predictions. Right now I'm not convinced this level of detail is necessary, but it's something I'm working on because I think it can provide, it just gets more into the details about what is going on in your time series. And what this is it's a minimization that's made available in stats models that has a simple interface, and really what it's doing is it's taking the whole time series and making a prediction of what the next time bin should be based on what the last few data points are and what the last few errors are. And then the integrated part also tries to account for patterns in the data, but I haven't quite figured that out and how to make it work and predict the daily and weekly patterns automatically that I've showed you in this talk. I'll just show you some results that I have there that are very preliminary that I'm still working to understand. But I need to find out why the fit is failing in certain cases. But when it is working, it seems to follow the data well, although this is on a log scale on this plot. So that's all I had to talk about. Here's the takeaways. Python provides simple and usable interfaces to most data handling projects. And combined, all those interfaces can really create a full data analysis pipeline from collection to analysis. And if you really like working with scientific computing tools like I do, then check Endgame out. We are hiring. So thanks a lot.